Word embeddings are a way of representing words and phrases as vectors. In the video on OpenAI Whisper, I mentioned how you could take text and convert it to a vector. What's fascinating about this concept is that when you take words and phrases and convert them to a numerical representation, words that are similar numerically are also similar in meaning. And this allows us to do things like build a search engine. In this tutorial, I'm going to show you how to build a semantic search engine using word embeddings. So you'll be able to build this application right here. I've generated the web app, so the front end for this application, using, of course, ChatGPT to generate the Python Flask code and DALL-E 2 to generate this little logo. So what I can do here is search through a bunch of different earnings transcripts. And so what I'm going to do is say demand for artificial intelligence is increasing. And so this is going to search an entire corpus of documents. And rather than trying to match just an exact string or an exact phrase, this is going to search for meaning in these earnings call transcripts. And so when I click search here, it's going to search the Microsoft earnings transcripts. It's going to return search results, and those search results are going to be ordered by relevancy. So when I search for demand for artificial intelligence is increasing, you'll see in this earnings call where Satya is talking about going further with new AI-powered capabilities, empowering automating natural language into advanced workflows. The second result talks about AI empowering DALL-E with Azure's OpenAI service. And the third result talks about cloud sustainability and so on and so forth. So how does this search engine work? How do we take these words and phrases that we see on a sheet of paper and convert them into numbers so that we can see the matrix behind everything and perform math on it and perform classification, anomaly detection, clustering, and all these cool natural language tasks? Well, that's what I'm going to show you today. I've prepared just for you this word embeddings notebook, and we're going to walk through how all this works, the math behind it, how to use OpenAI to generate word embeddings, and how to create a semantic search backend here step by step in a way that you can understand and apply. And we're going to build several projects on top of this. So this is highly important to understand. I'm going to do 3 or 4 videos using this exact same concept to show you different use cases. And I think this is one of the most fascinating concepts I've covered on this channel so far. So I hope you're as excited about it as I am. So let's go ahead and get started. Click the link down below and open up your Google Colab notebook to page 1 and follow along with me, and we'll walk through this line by line. So the first thing we need to do is install the OpenAI Python package, as we did in video 3 of this series. And so we're just going to run this cell right here that does pip install OpenAI. It installs OpenAI with the Python package manager. The next thing we need to do is import the Python packages we need. So we need to import the OpenAI package, as well as the pandas package for pandas data frames and NumPy for working with NumPy arrays. We're also going to configure our OpenAI API key. If you don't know how to get an API key, I covered all of this in video number 3. This series is building on itself, so I'm not going to go over that again. Get an API key, and you put it in this little prompt here, and it will store that, and OpenAI will be configured. And this allows OpenAI to track the number of API requests that you make. So to make sure we have a very clear understanding of this concept and how it works, I've started with a very simple list of words, and I've included a list of words right here. So this is words CSV. You see it has the words red, potato, soda, hamburger, cheesecake, mocha, fizzy, carbon, banana, things like that. And if I click raw here, I'll have a raw CSV file, and I can just save, I can do a save as in my browser, and I'll just save this as words.csv. And I'm going to download that locally right here. So I want you to download this Word CSV file, and then I want you to upload it to Google Colab. So if you go to the file browser here, I've already uploaded these, but I'm going to upload it again just so that you see this. And you should have a words.csv here, right? And once you have that words.csv file, you should be able to read that words CSV file into a pandas data frame. And now we have this variable called df. It's a pandas data frame that contains all of these words. The next thing we're going to do is calculate the word embeddings. What is this? This is what I said about converting these words into vectors. And so what we're going to do is use OpenAI to do this. And so if you were to look in the OpenAI documentation, there's a section on embeddings that tells you what they're for. And what it does under the hood is make an HTTP request, and you give it some words, and it actually returns this vector of numbers. So this embedding here, you see there's just a big series of numbers that's returned in response here. Now, rather than construct this API request like this, what we can do with the OpenAI Python package is import a function called getEmbedding. And the way this function works, you just pass it a string of text and you call getEmbedding and you pass it an engine. And we described the engines in the previous video. So there's the DaVinci, Ada, Curie, a bunch of different models or engines here, and you just pass the name of an engine. So for these text embeddings, we're going to use the Ada 002 engine. And these API requests are really cheap. They're like fractions of a cent to make. And so if you have a free tier already, you should be able to make tons and tons of these without worrying about it. Now this right here is kind of a complex expression. I understand it, a lot of people do, but maybe not everyone understands this lambda expression. So what I'm gonna do here is just run getEmbedding, this function by itself. Instead of X here, I'm gonna type an actual string. So I'm gonna type the fox crossed the road, right? Or whatever. And so if I do this, it's passing the string in and converting this sentence here, fox crossed the road, to a vector. So look at all these numbers that came back. So those don't mean that much to you, but they mean a lot to OpenAI. So they have these vectors that represent all these different words and phrases. And so rather than just running that once, what I want to do is run it on every single word in my corpus here. And so I have 26 words right here, and I want to convert all of them at once and create a new column with all of the word vectors right next to them, right? And so we're going to do this in batch. And so I'm going to take my data frame right here. So I have my data frame, and I'm going to create a new column called embedding. And inside of this column called embedding, what I'm going to do is store the result of this operation. So I'm going to take the text column. So this is the text column, and I'm going to apply a function to every single row in that column, right? And so what I'm doing is applying the getEmbedding function to each row in that column. And so the way these lambda expressions work, this is just a function without a name, right? And so for every single item in that column right here, that item is going to come in as X, and then it's going to say getEmbedding for that first word, and then it's going to store it in a new column. So it's going to getEmbedding for red, getEmbedding for potatoes, and then it's going to store the result right next to it. So that's how that function works right here. So after we have this new column called embedding, we're going to store those results in a new file called wordembeddings.csv. So why am I going to store that in a new file? This is so that we have this cached and stored. So we can store these word embeddings or these vectors in a database or in a flat file. That way we don't have to call OpenAI over and over again. And so storing this locally will save money and will save time. So anything that's not changing all the time, you want to cache it locally. So now that I have this word embeddings file locally, I'm going to open it up and look at what's inside of it. And now look at that. If you look at this, you'll see that not only is there text in the CSV file, there's a huge column of numbers here. So just for the word red, look at all those numbers, tons of them, like hundreds of them, right? And then just for the word potatoes, look at that, tons and tons of numbers right there. And so now what I'm going to do is take this word embedding CSV that I just opened and read it back into a data frame, right? I know I just saved it locally, and now I'm going to pull it right back out. And so now you'll see we have all of our text here and the word embedding that's right next to it. So every single word in this data frame has an associated big list of numbers. Wow, Larry, we have all these numbers. What do I do with them? Well, this is the part where it gets interesting. Let's enter a search term. And so I'm going to run this cell, and it's just going to present an input prompt, and it's going to say enter a search term. And I'm going to say hot dog here. And hot dog is not in this list of words at all. But what I'm going to do is get an embedding for this search term. So I'm going to get the numerical vector that corresponds to hot dog. So I'm going to make that call again and return that search term vector. And so this here, this in the matrix, this is what a hot dog looks like. This is a big list of numbers right there, right? And so now what I'm going to do is take this numerical vector, this numerical representation of hot dog, and I'm going to search through the numerical representations of all these other words I have cached in this data frame, and I'm going to find which vectors are closest to the vector for hot dog and search by similarity. And so let's go ahead and do this. And so the way I'm going to do that is I'm going to import a function called cosine similarity. And if you look up cosine similarity on Wikipedia or enter it into ChatGPT, you'll see that cosine similarity is just a measure of similarity between two sequences of numbers. And it's described by this equation. Now, this notation, this equation might look very complicated to you, or it might look very simple, depending on your level of math. But I assure you, it's actually quite simple. This is actually just multiplication. So this top term here is a dot product. And all this is just multiplying each of the terms in the two vectors together. And for those that want to perform this calculation manually, I've included this calculation at the bottom here. And so if you had this equation right here and you had two vectors, let's just say the first vector, v1, is just the numbers 1, 2, and 3. The second vector, v2, is just 4, 5, and 6. All you're doing is 1 times 4. So a1 times b1, 1 times 4, plus a2 times b2, 2 times 5, plus 3 times 6. And that's the dot product. So if you had 1, 2, 3, and 4, 5, 6, and you wanted the dot product, you could use NumPy to do that, or you could do this one by hand, right? So the dot product is just 32. And then on the bottom here, so you have the numbers 1, 2, and 3. So all it is 1 squared plus 2 squared plus 3 squared, and take the square root of that. So the square root of 1 plus 4 plus 9 equals the square root of 14. And the square root of 14 is 3.74, right? And so it's just a summation of a bunch of multiplications. You can even take these numbers here and put them into a 3D vector plotter here. And so if I put 1, 2, 3 here as a vector and 4, 5, 6 here, right? And I click draw here, and this is just some vector plotter I found online. You can see the vector 4, 5, 6 here, and the vector 1, 2, 3 right there. And you can see they're fairly close together. And so what we're actually doing is taking a vector representation of all these different words and seeing how close they are in space. Now, this is just a very simple vector of just 3 numbers. But if you look in our word embeddings file, you can see these vectors are very, very complex. So what does that look like on a graph? It's hard to really visualize that, and it's hard to perform this calculation by hand when there's that many numbers. Fortunately for us, there's a built-in function called cosine similarity that will run through all these numbers, multiply all the different vectors together, and perform this calculation for us. And then we can just sort all these different vectors out in space and find which vector is closest to hot dog. Let's do that right now. All right, so back to the cosine similarity of hot dog. So we have a search term vector. So this is the vector representation of hot dog. And what we're going to do here is take this cosine similarity function and apply it to every vector that we have in our data frame here. And we're going to check the distance between each one of these vectors and the vector for hot dogs. And so we're going to apply that calculation and store it in a new column called similarities. And so when I run this, it calculates all of those similarities, and we see our complete data frame right there. And so now all we need to do to find the words that are most similar to hot dog is sort all of those values in the similarities column, and then we're just going to take the top 20. And so when I sort this by similarities, you'll see the most similar words to hot dog are hamburger, cheeseburger, French fries, and cheese, which makes a lot of sense because these other words, it's not similar to water, not similar to milk, right? It's not similar to latte. And so it correctly identified that hamburger is the most semantically similar to hot dog just using these numbers. And then it calculates that cheese is fairly close as well, even though it's a little bit further down. And you can even see the color red is probably a little bit higher because maybe you could say a hot dog is kind of red and yellow is in the top 20. Maybe you could say the bun or something is kind of yellow, or maybe you could say there's ketchup and mustard. So maybe it's red ketchup and yellow mustard on the hot dog. And so it's really neat how you can use these vector calculations to find words that are semantically similar. Now, what's even more interesting about numbers is that you can add them together, for instance. So we can add two different vectors. So what happens when we take a copy of this data frame? So I'm going to make a new copy of this data frame that I'm going to call food data frame. And what I'm going to do is get the milk vector. So we have a vector for milk, which is in the 10th index here. So that's our milk vector. And then I'm going to take the espresso vector, right? So that's in number 19. So I'm going to take the embedding for milk and the embedding for espresso. I'm going to add them together. So I'm going to say milk plus espresso as numbers. And I'm going to add those and store them in a vector called milk espresso vector. So I've added two vectors for two words, and now I have a new vector called milk espresso vector. And so now I can apply the cosine similarity to the milk espresso vector against all the words that we already have. And so what's closest to milk plus espresso? Well, espresso and milk, because they're part of it, but the closest thing is a latte, which is a combination of milk and espresso. And so you can see when we sort this, we get espresso and milk, latte, mocha, and coffee. So I, for one, find that very fascinating if you've never seen this demonstrated before. So tying this all back into finance. So I wanted to walk through all of these calculations very slowly with words we're already familiar with, like colors, drinks, and food, and make sure we have a clear understanding. So I think that's a pretty clear description of what we've done here. Now let's figure out, how do we make our financial search engine? So let's go ahead and apply this same concept, not just to words, but to sentences, entire sentences. And so what I have here is a Microsoft earnings call transcript where Satya, the CEO of Microsoft, is talking about the latest earnings from Microsoft, right? And there's all these different paragraphs here. Now, instead of applying these word embeddings just to individual words, what we can do is take an embedding and convert this entire sentence to a giant vector. And what we can do is apply that same functionality. So I can type in some kind of phrase and then go through, calculate all those cosine similarities and find the sentences that are closest to what I typed in. And so that's how you can think about searching for a phrase or a term. And even though there's not an exact string match, we can find the sentence in here that's closest to what we typed. So now that we understand all the concepts, I'm going to go through this very quickly. So we can download the Microsoft earnings call, upload the CSV file. We read it into a data frame called earningsdf. Right there, you see all the earnings sentences in a data frame. Next, we're going to calculate the embeddings for all those sentences. So we're calling get embedding on each of the sentences here. And we're going to store this new data frame inside of a file called earningsembeddings.csv. If I open this, you'll see it's too large to display, but you can open this locally if you download it. So I'm going to search for a sentence. So earlier I typed artificial intelligence demand cloud products, just like that. That phrase is not going to be exactly like that inside of my data frame, but what we're going to do is convert artificial intelligence demand cloud products to a search vector. So we have a vector representing it, and then we're going to do our same thing. We're going to do the cosine similarity. So we're going to calculate the similarities of the earnings search vector that we just searched for. And then we're going to sort the values. And so when we sort this value and we open this data frame up a bit, you can see how it talks about Cosmos DB, DALL-E, Azure, OpenAI service, and so forth. You can see the second result here mentions the cloud, and it also mentions ambient intelligent solutions for automatically documenting patient encounters at the point of care. And then you can also see the third result here, now to data and AI, and it talks about the Microsoft Intelligent Data Platform. And so you can see this exact same concept we're able to apply here, and we're able to get search results for a particular earnings transcript. So now what you could do is build an entire search engine. So you can get tons and tons of text, not just finance, but whatever text you want, and load it into some giant database or some big CSV file or some flat file, and calculate these embeddings and make this search engine for your documents. Maybe your workplace has a bunch of documents, like some support documents, for instance. Someone mentioned maybe being able to automate customer support. So someone could type some question or query your documentation. And if you have this indexed and vectorized here, then you can build a search for that and return them the answers that they want. And so you can see how this is going to disrupt entire industries. Maybe you don't need a customer support person, or maybe you don't need a customer support form. I go on a forum and I type and ask for something and no one even replies to me. What if you could automate and at least give some type of reply, even if it's not the perfect one? Now, as a final example, I'll go back to our old friend, Jerome Powell. I've linked a CSV file containing the Fed speech that we discussed in the OpenAI Whisper video. So we talked about how these sentences impacted price, for instance. So let's say we have some new sentences and we want to see how similar they are to the ones spoken by the Fed in the past. Maybe there's some new sentences coming in on a live stream, for instance, right? And so what I'm going to do is read in this Fed speech that I've uploaded here. And now I want to get the embeddings for that Fed speech, right? And we're going to calculate those and store them in a CSV file called Fed embeddings. Then I'm going to input a sentence. And so I'm going to say, the inflation is too damn high. And then I'm going to search for everything Jerome Powell said that is similar to inflation is too damn high. What is the closest he has said to that, right? And so I'm going to get the embedding for the inflation is too damn high. And then I'm going to read my Fed embeddings CSV file back to a data frame. One thing I didn't mention earlier is that this part, apply eval NP array. Inside of the CSV file, this is just a string of numbers, but what we want to do is convert this to a NumPy array. So all that's doing is taking a string of numbers, using eval and then np.array and applying those, and that's converting it back to a Python NumPy array. So it's converting it back to like a Python data structure. So now I have the Fed data frame, and now let's calculate the cosine similarities and then go down here and sort, and let's see the stuff he said that's most similar to the inflation is too damn high. So if I open this puppy up right here, how does Jerome Powell say it? He doesn't say the inflation is too damn high. He says Recent inflation data, again, have come in higher than expected. So higher than expected, inflation remains well above our longer run goal of 2%. My colleagues and I are acutely aware that high inflation imposes significant hardship, or the longer the current amount of high inflation continues, we are highly attentive to the risk of high inflation, right? And so all these other ways of saying the inflation is too damn high, and we're able to search a speech for that meaning using these vectors of numbers. So pretty cool. In about 20 minutes, we learned how to make a simple search engine as well as the math behind it and how to use OpenAI to calculate these embeddings to find similar words and phrases. In the next video, we're going to take advantage of ChatGPT and DALL-E to make just a simple front end and a simple logo in case we wanted to productize. If we want to make an AI product, we can take a front end, put it on this back end, slap it together and deploy it to a server, and we got a cool little search engine. We could load tons of text into it and make the next CNBC or Seeking Alpha or whatever you want to make and sell it for millions of dollars. So that's it for now. Thanks for watching. See you in the next one. Thanks.